Yeah, yeah, so we are back for another presentation in this year's Limit Camp. For this segment, the speaker is obviously my friend Aaratrick Basu. He is pursuing a PhD in University of Virginia, USA. And as his title suggests, he is going to show us how to play ping pong like group theory. Yeah. He is interested in topics involving geometry and topology. Uh, so I think today's talk will be something involving those. Over to you, Aaratrick.
Thank you. Thank you for the introduction. So this talk will, as I mentioned in the abstract, this talk is going to be an introduction, a gentle introduction to the field of geometric group theory, which, it's a little bit more advanced than just group theory. We try to understand groups by understanding how they act on certain geometric spaces. So one of the important classes of groups in this field is what are called free groups. So this talk is going to be an introduction to some of their basic properties and how you can recognize free groups inside abstract groups. So let's begin. So I wanted to begin with this quote that I really like due to Joseph Rotman. It says, "A valuable technique in studying a group is to represent it in terms of something familiar and concrete. After all, an abstract group is a cloud. It is a capital letter G." So given just an abstract group, it's often not possible to get any information about it unless it's a very simple one. So we often try to understand abstract groups by trying to understand how they act on objects. So let's briefly recall the definitions. So what's a group? So a group is a non-empty set G equipped with an associative binary operation dot, which we often omit and just write by concatenating the two symbols, and a distinguished element E inside of the group called the identity, so that for all x in G, EX equals XE equals X, and for all x in G, there is some Y such that XY equals YX equals C. So here, of course, when I'm writing EX, I mean E dot X, and XE, I mean X dot E, and so on. And moreover, what's an action? So an action of a group G on a non-empty set X is a group homomorphism theta from G to the group of bijections of the set X, which we denote as sim of X. So what's a group homomorphism? It's simply in this case at least, it's just an assignment G maps to theta of G, so that the identity will map to the identity map of the set X, and theta respects the group structure in the sense that theta of GH should be theta of G times theta of H, where the multiplication on the right side is given by composition of two functions. And this relation should hold for all group elements G and H. Right. So we need a little bit more. So a priori, a group action is only defined for sets, right? You have a group and you want to say when it acts on some set. But what if your set X has more structure? So if you just have a set, really you can only ask for bijections of that set to itself. But for example, suppose you have a graph. So I know there have been a couple of talks on graphs, so this should be familiar. So a graph is a set of vertices and a set of edges, where the edges are sort of pairs of vertices. And so we can talk about graph automorphisms. So what are graph automorphisms? So you can think of graph automorphisms as bijections on the vertex set to itself, such that it respects the adjacency, in the sense that if you have two vertices that are adjacent, then images should also be adjacent, right? So then if you want to define a group action on a graph, you want to make sure that the group elements get assigned to graph automorphisms, not just abstract set maps. Because the big idea is that a group action should be an assignment of structural symmetries. So there's a typo here. There should be an E here. Yeah. So of structural symmetries of some object to the elements of our group. So when you want to study a group by looking at how it acts on an object, you want to make sure beforehand that the group respects some kind of structure on that object so that you get more information. Right. So now let's move on to the main definition. So we start with just any non-empty set X, and we consider the set of words. in the elements of X. So what are these? So these are just strings of letters where the letters can either be elements of X or formal inverses. So what we are doing is we are sort of taking two copies of our set, and one copy we are sort of designating as the set of formal inverses. Like there's no meaning to like X inverse, but we just introduce a new copy for each element X in our capital set, in our set capital X. We introduce a new element X inverse. It doesn't exist before that. We just introduce it formally, right? And we consider strings of such characters. So I'll do an example shortly, and that would make it clear. But it is what you're thinking of. You just have some alphabet, some set of elements, and you just take sequences of those elements. And we introduce an equivalence of such words. So the equivalence is, again, pretty natural. So we just identify words of the form U, X, X inverse V with the word UV. So whenever you have some phrase and its inverse appearing consecutively, you cancel, so to speak, and you sort of shorten that word. And you will say that like introducing these redundancies, like some phrase and its inverse anywhere in your word consecutively should not affect your equivalence. That's the equivalence relation. And we also introduce some notation. We set X to the power n for some word X, not necessarily just an element, but any word, to be just that that word concatenated n times. Right. So how do we get the group? So the group here is the set of equivalence classes. So you look at all the words and then you collapse. You pick, for example, one representative of each equivalence class. And for example, there is a unique equivalence class of the empty word. Like the empty word is you take no elements at all, right? It's the empty word. For example, any word X inverse is equivalent to the empty word. So you designate the class of that empty word as your identity element, E, and the binary operation here is induced by the concatenation of words. So it's not really obvious that what you do end up with is a group. You have to check associativity and that the identity behaves like the identity, the inverse behaves like the inverse. But it's a routine exercise, and I didn't want to do that here. So let's just assume, let's take it for granted that what we end up with is a genuine group, like all the group axioms are satisfied. So we denote, so if we, oh, again, there's a typo. If you start off with a set X, then the group that you obtain in this way is called the free group on X, and it's denoted by f of X, capital F of X, right? So let's do some examples. So suppose you have the set has only one element A. So what are some words, right? And feel free to sort of stop me whenever you have a question, but yeah. So what are some typical words? So you have the empty word, you have the word given by the single character A, you have the word given by the single character A inverse. So remember, A inverse is just a formal inverse that we're introducing. You have the word A squared, you have the word A inverse, you have the word A. So really I should write A, and so, maybe A inverse A, and so on, right? All of these are words. Now, when you collapse, for example, this word becomes A cubed, this word becomes A squared, this word is again the empty word, this word is again A, and so on, right? So if you think about it for a little bit, it should not be too hard to see that f of X is something like E, A squared, A cubed, so on, and then A inverse squared, A inverse cubed, and so on. Right? So this should be familiar. Like this should be familiar to anyone who has seen groups before. And this is exactly the infinite cyclic group, right? It's the infinite cyclic group. And this, so when we start with a set with only one element, which we denote as A, it can be anything, of course. Then we get the infinite cyclic group by looking at the free group on that set, right? So let's do something a little bit more interesting. Suppose you have two elements in your set. So you might think, okay, maybe this is we just did one element or two elements. Is this boring? But no. Well, there's a lot of group theory in just f of X where X has two elements. So what are the words, for example? So again, you have the empty word, you have every word that you had before, A inverse, A, so on, and similarly you have B inverse, B, and so on. But you also have words like AB. You have a word BA. You have a word BA inverse B, and so on, right? These are also words now. The main thing to notice is that if you look at the equivalence relation that I mentioned, this word and this word are not the same. AB, you cannot go from AB to BA by just introducing XX inverse in the middle, right? Like for any X, a word in W. So when you collapse to the equivalence classes, you will see that you still have things like, so you have everything that you had before. So E, A inverse, A squared, A minus 2, and so on. And then B inverse, everything like that. You have an element AB. So, okay, maybe I should also mention this. I'm abusing notation a little bit. I'm sort of denoting the equivalence class of AB by AB again. You again have an equivalence class corresponding to BA, and these two equivalence classes are distinct. They're not the same. You have an equivalence class corresponding to BA inverse B, AB inverse A, ABA, and everything like that, right? Okay. You also have things like, for example, A. So if you were looking at the word, for example, ABBA, this gets collapsed to AB squared A, but that's it. There's nothing more that you can do. AB squared A is not the same as, for example, B squared A squared or anything like that, right? Is that clear? Is there any question so far? Okay, then maybe I should.
When
Yeah,
you mentioned
sorry.
that not of the same equivalence class, what do you exactly mean?
So, okay, what do I mean by that? So I meant that so two things are in the same equivalence class if they're related by this equivalence. And so I'm saying that AB and BA cannot be related by this equivalence when I say that they're not the same equivalence class. Does that answer the question? Okay. Right. So there's a small fact that we need, which is also not that hard of an exercise, based on what I've just told you, and some basic facts about groups. So, or maybe, yeah, I'll mention one more fact which might make this a little bit easier. So, if X and Y are any two sets of the same cardinality, then what do I mean by same cardinality? First of all, so if they're finite sets, you can just literally think of them as having the same number of elements. But for infinite sets, you need to be a little bit more careful. Here, by same cardinality, I just mean that there is some bijection phi from X to Y, right? So if X and Y are any two such sets, then the free groups f of X and f of Y are isomorphic as groups. So what I mean is that there's a group isomorphism from f of X to f of Y. And in fact, okay, well, I'll talk about that in a short bit. But so we introduce some notation. We denote the free group on any set with n elements, which we can because of this fact, as f of n, f sub n. Sorry. So for example, this X being the two element set, the group that we get here is F2, and the group that we got here was F1. So what we have just shown here is that F1 is the same as the infinite cyclic group. So far at least it's not obvious to me from here what F2 is right as a familiar group, because there's just some sequence of elements. It's not really obvious what kind of group this is. Yeah, I don't see an obvious pattern at least. So we'll by the end of this talk, I hope to convince you that this is a very interesting object and it's hard to understand. So let's proceed. So a little bit of a digression. Why free? So the idea, the terminology free is sort of explained by the following theorem / fact. So if X is any set and G is any group, if you have any function, so just a map of sets, X to G given by small phi, then there is always a unique group homomorphism capital Phi from the free group on X to G, such that the following diagram commutes. So there's two things. One is there exists this phi, capital Phi. There is such a thing that you can sort of explicitly define. in terms of small phi, and it's unique. So you can only, like, once you write it down, that's the only way to do it. You can't have any variation in there. So what is this diagram saying? It's saying basically, so the first thing to notice is that any set X embeds inside. So there's a map from any set X to the free group f of X, just a map of sets given by, because like you just map every element to the corresponding equivalence class, right? Again, no two elements of X can be equivalent. They all belong to distinct equivalence classes. That's also sort of easy to see from the definition of the equivalence, but yeah, that's another fact. So that gives you this map, and you have the data of the theorem says that there is a map small phi going from X to G. This capital phi is saying that when you restrict phi to the copy of X that lives inside the free group, you get back the small map phi. That's what this diagram is saying. And so this is why free, because in some sense your free group is like, if your set sits inside any group, your free group on that set must also sit inside. So sit inside is just in the sense of there is a map. It's not necessarily injective. Just, yeah, there is a map, right? So that's the reason why they're called free. And so another bit of notation, we say a group is free if there is some set that you can find for which it's the free group on that set, right? Okay, so we want to understand free groups. So as I mentioned, we have already seen that F1 is the same as the infinite cyclic group. And we maybe by the end of this talk, we want to see what we can say about the free group on two generators. So the free group on a set of two elements. So for that, we need another, like one of the ideas that I wanted to introduce was the Cayley graph. So that is defined as follows. So suppose you have a group G and you look at a generating set. So what's a generating set? So generating set is a subset of your group for which any element of your group can be expressed using the elements in your set F, in your distinguished set F. So of course, you can always take F to be the full group G. That's okay, but you want to sort of look at the simplest possible in some sense. Usually we want, at least in terms of geometric group theory, we usually want to restrict to the class of groups for which there is some finite generating set for that group, right? So let's do an example. If you look at the group Z, then one way is to take the generating set given by 1. So here any element n can be written as n times 1, right? Because which is like 1 plus 1 plus up to n, right? N times. You can always do that. So this proves that this is true for any integer, and 0 is like 0 times 1. But you can also take a generating set given by the set 2, 3. So how do we do that? So you want to say that any integer can be written as something of the form 2x plus 3y. So this is indeed possible. This is Basu's lemma that says that because 2 and 3 are co-prime, any other integer can be written as some number of 2's added together plus some number of 3's added together. And so indeed, 2, 3 is also a generating set for the infinite cyclic group. Right. So so that was it for the example. We go back to the definition now. So now suppose again we have a group and you have fixed some generating set S inside it. The Cayley graph of the generating of the group G with respect to the generating set S is a graph which we denote as K G comma S. Oh, sorry, I wanted to use other colors. K G comma S is a graph with vertex set given by the elements of your group and H set given by things of this form. So you connect two elements G and H, which are now vertices, by an edge if and only if there is some generating, like element S in your generating set such that excuse me, either G is H times S or H is G times S. So the idea is if you can go from G to H or H to G using only one element of your generating set or its inverse, because H equals GS is of course the same as HS inverse is equals to G, right? So that's the idea of the adjacency. You want to connect things that are only one generating element apart. So let's do an example because this is maybe a little abstract. So the example here is again, let's take the infinite cyclic group with the generating set given by just the element 1. So then every element is just 1 times the previous one, right? 1 plus the previous one. So 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, and so on. And similarly, minus 1 plus 1 is 0, minus 2 plus 1 is minus 1, and so on, right? It's just a straight line, right? Is this clear how this is k z comma 1? This graph is k z comma 1. Oh, by the way, I should mention the Cayley graph is named after Arthur Cayley, the same guy after whom Cayley's theorem in finite group theory is mentioned, is named. So yeah, so is it clear why this is the Cayley graph with this generating set for z? Okay, I think yeah. Feel free to ask a question if you have. So let's do a little bit more interesting. So now suppose you look at the same group z, but now you change your generating set to this set 2, 3 as I mentioned. So what does the Cayley graph look like? So I claim it looks like this. So we have edges of 2 types basically, one given by adding or subtracting 2, and one given by adding or subtracting 3. So if you focus here, 0 plus 2 is 2, so you have an edge like this. And 0 minus 2 is minus 2, so you have an edge like this. And similarly, you have 0 plus 3 is 3, that's this edge, and then 0 minus 3 is minus 3, right? So you have this edge. So notice how here 5, you have to go to first 2 and then 3. Sorry. You first go to 2 from 0, and then you go to 5 by adding 3. You can't go from 0 to 5 directly, so to speak. So, but here, if you wanted to go to 5, you had basically only one option. If you wanted to go as fast as possible, in some sense, like you go 5 times in the right direction, and then but here you have to go like this. So now, so I won't be precise about this, but what I'm saying here is that the distance of 0 and 5 in this graph is 5 units somehow. And the distance between 0 and 5 in this graph is now 2 units, because I can do it in 2 steps, right? First I go to 2 and then I go to 5. So the distance is changing. So there is, in some sense, the graphs should be different, right? Because if the graphs are the same, this distance would be the same. Like the fastest possible way would be the same. Well, that's not quite true. Like Cayley graphs of the same group with respect to different generating sets can be different. But there is a big idea in geometric group theory where these two are considered the same. And this idea is basically you squint your eye, look at the graph from afar. Like suppose you had this graph and you sort of moved back. If you moved really far back, these sort of orange and blue lines would sort of blend together to give you a flat line, like roughly flat line, right? And that is basically this graph, right? Which is a flat line. So this idea of sort of squinting your eyes and looking at things from far is a very, very powerful idea of geometric group theory, due originally to Gromov in the 70s, but even further before people had some different interpretations. But yeah, so I won't go into much detail about that. But again, that's another interesting idea, I think. Okay, so let's come back to our main character, the free group on 2 generators. So I claim that this is the Cayley graph with respect to the obvious generating set. So we are looking at the free group on the generating set on 2 generators A and B, and we take those elements A and B as our generators. So what is this graph saying? So let me trace this out. So you have this identity element given by the empty word. You can either sort of go to the multiply on the right by A, or you multiply on the right by B, or multiply on the right by A inverse, or multiply on the right by B inverse, right? So there's 4 ways to go from E. There's nothing else that you can do. You have to multiply by either A, B, A inverse, or B inverse, right? That's the definition of edges in your Cayley graph. Now suppose you are at now A. Again, you have 4 options. You can multiply by A inverse on the right, that gets you back to E. You can multiply by A on the right, that gets you to A squared. And if you keep proceeding, you get A cubed, A to the 4th. And if you go to the left, you get A inverse, A to the minus 2, and so on. But more interestingly, you can also multiply by B on the right. That gets you up here, right? That gets you here. or you can multiply with B inverse, that gets you down here, right? And similarly, at every point, you have 4 choices. I've only drawn 3 here because of lack of space, but there is another edge here, there is another edge here, and every vertex has 4 edges given by, I multiply on the right by A, B, A inverse or B inverse. And the fact is, and which you can sort of verify formally from the definition of the equivalence of words that I mentioned before, that there's only these obvious ways of going back. Every, like, sort of at each vertex, there is one way, one of the 4 ways sort of gets you back to a previous vertex. But each of the 3 new ways, so multiplying by 3 of the other possibilities, gets you a genuinely new vertex, a genuinely new element of your group. And the fact is that because you can do this at every vertex, this is what we call a 4 regular tree. So there's 2 things that I want to say. So what's the 4 regular? So 4 regular means that every vertex has 4 edges connected to it. And tree, which is more interesting, is saying that there's no loops. You never, if you keep walking and if you keep taking like a shortest path, a geodesic, if you know what that is, you take a path of shortest distance basically between any 2 points, you will never come back. You never see a loop. You never visit a point that you had already visited before. You're very efficient in some sense. That's what's a tree, like a graph with no cycles. You never see a sequence of edges repeating to the same vertex unless you already repeated an edge as well. So it turns out that it can be again checked formally that this graph, like the Cayley graph of the free group on 2 generators with this generating set, is indeed a tree. So the big idea, one of the big ideas in geometric group theory is we try to understand a group G by looking at how it acts on the Cayley graph. So what do I mean by this action? So let me come back here. So as I mentioned, every time you have 4 possibilities, you multiply on the right by one of A, B, A inverse or B inverse, right? But imagine instead of just multiplying by one of these, you multiplied by some arbitrary word W. Right. So for example, if your word W is say A, B, A, and you multiplied W on the right to E, what do? You sort of start reading your word from the left. So first multiply by A, that gives me here. Then multiply by B, that gets me here. And then again multiply by A, that gets me here. So this ABA, this vertex is the same as if I multiplied E on the right by W. So I'm just putting the dot here to sort of emphasize that I'm multiplying E by W here. I can think of this in another way as sort of saying that W acts on E like this. It turns out that this indeed gives you an action of the group on the Cayley graph, like in the sense of that it acts by graph automorphisms, and it can be verified that it can be verified that the assignment is a group homomorphism into the automorphism group of the Cayley graph. And so you sort of get, whenever for any group and any Cayley graph, you always have an action of that group on its Cayley graph. And so the big idea is to try to look at this action because oftentimes we can get a lot of information about actions on certain kinds of graphs, and so try to understand the group from there. And so one of the important theorems in this line of thought that I wanted to briefly mention, because I feel that this is a beautiful theorem, is that a group G is free. So by which I again mean that there is, so here I mean there is some, so there is a set X such that G is isomorphic to f of X. That's what this means. If and only if there is some tree, so like I defined, it's a graph without cycles, and an action of the group G on the tree freely. So what does this mean? So this means that if G is a group element that is not the trivial element, then G dot V is not equals to V for every vertex V, and there is no group element which only flips edges. So what do I mean here? So what I mean by this is, so let me draw a picture here. So U, V, and you have some, this is an edge, right? So suppose you had a group action that sort of did this. It just flipped V and U on this edge. And it did the same, like when if you had a group, so you had a group acting on some graph, and what by this I mean that there is no element that, for which what it does is only flipping edges. So it turns out that that sort of leads to a trivial sort of problem, but you don't want that. So these two conditions together is what we mean by a free action on a graph. And so this theorem is saying that a group is free if and only if it admits a free action on tree, right? So I think this is a powerful and beautiful theorem because we wanted to understand free groups, right? Because the definition is abstract. It's not really clear what happens when you have more than one generator. And this is a beautiful way of trying to understand it because we always have some graph on which the group acts, namely the Cayley graph, with respect to some generating set. You may have multiple graphs even. Of course, so sort of it's not hard to show based on the ideas that I displayed here that whenever you have a free group on some number of elements and you look at the generating set given by the set on which it's free, then you will always end up with a free graph you'll always end up with a tree as the Cayley graph. But the converse is harder, to show that there is always some tree on which a free group acts, on which a group acts freely. That implies that actually has to be free, right? Okay, so yeah, don't feel scared if you don't understand this, because this is a hard theorem. It's not obvious at all. So I just wanted to mention it because yeah, this is I think one of the beautiful ways to understand free groups, right? Okay.
Can you explain the
So-
round arrow notation?
Yeah,
What
sorry.
is the arrow notation stand for? G round arrow to T.
Oh, this just means that G acts on T. So there is some group action of your group G on the tree T by graph automorphisms. That's what it is. Yep. Okay. So now let's move on to the main sort of advertised theorem, the ping-pong lemma. So this is due to Klein, Felix Klein originally, but perhaps Poincaré also knew it, but we don't know. So the theorem goes as follows. So let G be a group and X is any non-empty set again. And suppose you have some action. Now this is just an action of a group on sets. Oh, someone is asking why is it hard? Try it. Try and see why it's hard. It's yeah. There's something you need to know about free groups. It's not obvious from the definition, but yeah. But okay. So let me come back to the theorem. So suppose you have a group action on some set here, and it's just a set. There is no additional structure assumed. And suppose you have disjoint non-empty subset U and V inside of your set X, and two elements G and H in your group, such that G to the n for any non-zero n pushes U inside V, and H to the n for any n non-zero again pushes V inside U. So I'll display an example shortly, but the theorem is claiming that whenever you have such a thing happening, the subgroup G comma H, so this is the subgroup generated by G and H inside of your group G. So this is like all possible products of G and H inside of your group. So there can be non-trivial things that collapse. Like it might just happen that H is G inverse. It can't happen under these assumptions, but so then this would just be the intrinsically group. But if that was true, but it won't happen under these assumptions. It's saying that if you look at this subgroup, this is free, in the sense that it is isomorphic as a group to F2. So again, I think this is a beautiful theorem, and I think it's the closest analogy I can think of is it's akin to the pigeonhole principle, in the sense that actually proving that this theorem holds is not that hard. I will do a proof shortly, but it's really the difficulty lies in trying to apply this in the wild. When you have a group and maybe that group comes to an action on some set, on some topological space or some other vector space, maybe some graph. How can I find two such disjoint subsets U and V and elements for which this is satisfied? That's the hard bit. And of course, it's not at all trivial, and really, it's sort of an art to come up with those constructions. And time permitting, we'll do 2 examples, but yeah, maybe you'll appreciate that it's hard. But okay, so what was this bit saying? That G to the N pushes U inside V, and H to the N pushes V inside U. So this is a pictorial representation. So let me maybe switch colors. Yeah. So suppose, so what I was saying was, oh, this is not that one. Maybe. So what I was saying is G to the N pushes U inside V, and H to the N pushes V inside U. So what is this thing? So suppose you have, suppose this, the region demarcated by this blue line is U. You hit it with G once, it gets you to somewhere inside of V. So this region demarcated by the pink is V. Now, if you hit it with H, you get something here. And then if you hit it with G again, you go here. And if you hit it with H again, you go here. So every time it sort of penetrates deeper and deeper into the original 2 sets U and V. Of course, there's a pictorial representation, and this need not happen literally, but this is sort of how you should try to understand this condition. That roughly speaking, of course, I don't know, I don't play ping pong, maybe that's why I think of it like this. You have a ping pong court, and every time you get the ball in your court, you have to sort of get it to the other side, and then this goes here, and then that goes here, and so on. Keeps on continuing like that, right? So that's the sort of understanding here. So I hope that the conditions of the theorem are clear. So let me just briefly review that one more time. You just started with a group action on some set, and you're given, somebody has told you that there are 2 non-empty disjoint subsets U and V and elements G and H, for which G to any power pushes U inside V, and H to any power pushes V inside U. By the way, it's not trivial to just, it's not enough to just assume that G and H itself pushes the respective things to the respective things. You have to assume it for all powers. Then the claim is that the subgroup generated by G and H is actually free on 2 generators, right? So let's do a proof. It's not, like I said, the proof is sort of like, you do the obvious thing and it works. And so how do we start? So first of all, notice that since G to the N pushes U inside V, and U and V are not the same, and they're non-empty and disjoint, this has to mean that G to the N is non-trivial. It cannot be the identity element, right? Because like a non-ident, like only the an identity element cannot push something to something else. That's just not possible, because one of the axioms of a group action was that the identity is always assigned the identity map, right? And similarly, H to the N is also non-trivial for any power n, non-zero. Now you look at any arbitrary word W in your subgroup generated by G and H, and for simplicity, I've sort of assumed that this word, because we've already dealt with G to the N and H to the N, we can assume that this word is not just some power of G or some power of H. So there are 4 cases. Suppose you have a word which starts and ends with G. So it starts and ends with G. So what do I mean by reduced here? What I mean by reduced is, if you look at, so it's not like none of these exponents are 0, and you sort of don't have any collapse, like, yeah, none of these exponents are 0. That's enough to say. Yeah. You've sort of collapsed all the powers of G together, all the powers of H together as much as you can to get this word. That's what I mean by reduced, right? So suppose you have your word satisfies that it starts and ends with G. Then if you look at W of the set V, this power of G will push V inside U, right? So then W of V is contained inside this word up to H to the NK, mapping U, right? Acting on U. But now H to the NK will push U inside V. So that gets me back to the last term, which is MK minus 1. So now again, we have a word starting with G and ending with G, but notice that the length has gone down. Because these exponents were all non-zero, the length of my word has gone down. Like I have fewer G's now, for example. So by induction, or just by formally it's induction, but you can also sort of see it as just you keep repeating it as many times as you can. You end up with W of V is contained inside G to the M0 of V, but that again by assumption has to be inside U. So then W also pushes V inside U if it starts and ends with G. But again, that means that it's non-trivial, right? It's non-trivial. Yeah. Yep. So similarly, if your word starts with H and ends with H, you conjugate by G to the M0, for example, just to make sure that we don't have any redundancies. Then you see that this word is now G to the M0, H to the M0, and so on, G to the H to the MK, G to the minus M0. So now it starts and ends with G. So by case one, we get that this word is non-trivial, but if a conjugate of a word is non-trivial, that word also has to be non-trivial. Like this is again basic group theory. And then finally, the last two cases are sort of simpler. If you have a word that starts with G, ends with H, again conjugate by G, you'll see. So this exponent becomes 2 times M0, and then you get a minus M0 at the end. And again, this is starting and ending with G, non-trivial. So then W is non-trivial. And finally, if you have a word that starts with H, ends with G, the inverse is a word that starts with G, ends with H, because of course the MIs and the NIs are arbitrary integers. They can be negative. So then W inverse is non-trivial, and so W is non-trivial. So then any non-trivial word in my subgroup G and H is actually it cannot be the trivial element E, the identity, and so this group is actually the same as the free group on the generators G and H, which is again F2, right? Is that fine? Any questions on this? So like I said, you sort of do the obvious thing and it works. But now, so in the last 10 minutes or so, I want to sort of illustrate the difficulty, so to speak, of trying to apply this result. So we look at the group of 2x2 matrices that have integer entries and determinant 1. So these are matrices A, B, C, D, for which A, B, and C, D are all integers, and the determinant AD minus BC is 1. Right. So this is our group. What does it act on? It acts on multiple things, but for today we want to look at the action on R2. The action on R2 is just by linear maps. So ABCD. Oh, someone is asking. Yes. So there is a generalization of this result for Fn. In fact, so if you sort of Google the ping-pong lemma, then you will see, for example, the version on Wikipedia is far more general than this. But I didn't want to complicate things unnecessarily, and this is sort of the crux of the proof is the same. Once you know how to prove one version, you can prove any other version. And yes, there is a generalization for Fn in particular. Yes. Okay. Yeah. So excuse me. So the action is by linear map. So ABCD acting on the vector XY in R2 will be AX plus BY in the first coordinate and CX plus BY in the second coordinate. So this should be familiar. So what are the candidates for our free group generators? So G is this map 1, 2, 0, 1, and H is this map 1, 0, 2, 1. So you can, this is like an easy exercise to see that G to the N for any N is 1, 2n 0 1. Similarly, H to the N is 1 0 2n 1. In particular, if you notice G to the N acting on XY, so I'll omit the dot now, is just x plus 2ny in the first coordinate and y. So it doesn't do anything to the second coordinate and adds 2n times the second coordinate to the first coordinate, right? And similarly, maybe I'll just mention this for completeness. This is x, and this is 2nx plus y. Great. So far, so good. So now we have to cook up the sets U and V. So again, it's like I said, it's sort of an art to cook those sets up, and it's not like you don't get a prescription. You sort of have to do it as you go. So for example, here two sets that do work are the following. So you look at the plane, XY plane, and you look at the set U given by absolute value of X is less than absolute value of Y, and the set V, which is given by absolute value of X, is greater than absolute value of Y. So remember, it's not true that U union V has to be the full set. It's just enough that U and V be disjoint non-empty. You don't have to look at a partition of your set. Oftentimes that can also work, but you don't necessarily have to do it. So it doesn't matter that U union V misses this sort of crisscross line. Yeah. Now the point is that G to the N indeed pushes U inside V, and H to the N pushes V inside U. So why is this true? Let's do a quick computation. So suppose X comma Y belongs to U. This of course means that absolute value of X is less than absolute value of Y. Then if you look at G to the N times the vector XY, from the last slide, we know this is X plus 2, last page, not slide, X plus 2 Y comma Y. So if we want to show that this is in V, so we want to verify this. So if you look at mod of X plus 2 Y, by the reverse triangle inequality, this is bigger than mod X minus, actually no, I think 2 times mod N times mod Y minus mod X. So you know, this is fine. This is greater than equals 2 times mod N mod Y minus mod Y, because this implies that minus mod X is greater than minus mod Y, and that's what I've used here. I replaced this minus mod X with minus mod Y, so I get an inequality here, and so this is 2 times mod N minus 1 times mod Y, and yeah, because N is a non-zero integer, this is at least 1. This is always at least 1. And so you're done. Your first coordinate is strictly bigger than the second coordinate, which is the definition of the set V. So similarly, you can check that H to the N times acting on V will push it inside U, right? So like I said, there's no prescription to do this. You just have to do it as you go. Here, we utilize the fact that on R2, we have this nice metric structure, which we can exploit so a priori, the group SL2Z acting on R2 is just a group acting on a set, but we're exploiting extra structure. The ping-pong lemma in the assumptions, there's no demand for extra structure on X, on the set that on which your group acts. But what you often need to use to apply the lemma is the extra structure that's available, and also maybe information about your group that you know beforehand. So yeah, for example, here sort of from linear algebra, we know a lot about how matrices act, for example, on R2, right? So that's what we're using here. So this completes the proof, because now the ping-pong lemma is satisfied, and so G and H have to be generated free group, right? Is that fine? Okay. Yeah, that should be pretty straightforward. So for the cognoscenti, this is like a much more general result due to TITS. It says that if you have any matrix group over any field, not necessarily the reals or the complex, that has some finite generating set, then either G is a solvable group or contains a copy of the free group on 2 generators. So there is a very, very powerful result, and it's called the TITS alternative. And a lot of work in geometric group theory is sort of trying to find different classes of groups where this criterion is actually satisfied. And once you know this, you get a lot of information, because we know a lot on how to study solvable groups. And once you know that your group contains a copy of your free group on 2 generators, you know that your group has to be a certain level of, it has to have a certain level of complexity, so to speak. It has to behave in a certain sort of non-trivial way wherever it acts. That's the sort of big idea. And so, yeah. Right. So I think I have 5 more minutes. So let me quickly go over one more example, just to show that, like I said, the techniques needed to apply the ping-pong lemma can vary, and sort of also that free groups are ubiquitous. Like matrix groups, again, you already know that there's so much structure, but here I wanted to say that you can get free groups in pretty, like, a bunch of different groups. So let G be the group of say bijections of R, right? Just bijections work, order preserving bijections work. If you know what a homeomorphism is, homeomorphisms work, order preserving homeomorphisms work. In fact, order preserving homeomorphisms of Q also work. Like G can be anything like that. Yeah, and X be the set R. So if you are looking at Q, then you replace here with Q. Look at this transformation of the unit interval that takes T to 4T if T is less than 1 over 5, and to this 4 over 5 plus 1 over 4 times T minus 1 over 5 if T is more than 1 over 5. So the picture is much better than this formula. The graph of F is like this. So it goes like very sharply here. This is 1 over 5, this is 4 over 5, and this is 4 over 5, and this much is 1 over 5. So yeah, you can sort of think of it as like you have this sharp spike here, and you sort of flatten it, sort of rotate it, and get here, right? And also the translation x goes to x minus r. So this is my capital F, this is my capital G. Now you define two elements f of small f and small g as follows: the floor of the integer part of x times this transformation f, capital F, applied to the fractional part, which is like you take your x and you subtract of the integer part, you get the fraction part, and you apply your capital F to that. And small g is defined as you conjugate your small f by this translation capital G. Right. So yeah, there's not much I can do to illustrate these, but yeah, it's sort of you just look at the formula. You can work out explicit formula for these if you want in terms of just the integer part, but yeah, that's not really helpful. So what are my sets U and V? So the sets U and V are these union of these sort of length 2 over 5 intervals about the integers. So let me draw a quick picture. I should have maybe drawn this picture before. So 0, this is minus 1 over 5, 1 over 5. So this is 1. And then, for example, if you have 1 here, this is 4 over 5. And then, 6 over 5. This is k equals 0. This is k equals 1. And you have copies like this, so on. You take all of these and you take the union. And you look at this union and you hit it by the translation x goes to x minus r. That's my capital G. The image is going to be this union, and because you were looking at these intervals centered about integers, each of these intervals is actually going to be disjoint from each of these intervals as well. That can be verified. And so you indeed get non-empty disjoint sets U and V. Again, the union is not really all of R. But okay, so what can we say? So the key observation is the following. If you look at this transformation capital F and maybe this formula, you can, and I think it's easier to convince yourself by looking at this graph and sort of trying to apply this multiple times. If you hit the interval 1 over 5 comma 1, so this bit, by F as many times as you want, positive powers, then that has to be contained in the interval 4 over 5 comma 1. And similarly, if you hit it with its inverse, hit this interval 0 comma 4 over 5 with the inverse, sort of you take this figure and you flip it, right? So then this is the interval in question. As many times as you hit it by the inverse, it's always going to be contained inside 0 comma 1 over 5. And so with this, a straightforward calculation will tell you that this map, small f, will push this capital V inside capital U. And then by the way, small g is defined as conjugation by the translation capital G, you do this, like you express your things like this, and that things cancel off, and you're left with G of U. Because you will use this fact to get G of U, and then that's V. So again, this completes the proof that because the ping-pong lemma assumptions are satisfied, and so we automatically get that small f comma g has to be free on two generators. Right. So yeah, that's all I had to say. Thank you. Thank you for your attention. Yeah.
Thanks, Aaratrick, for
Yep.
your wonderful talk. Yeah, so we're it's the last talk of limit camp. So before we conclude, we can take a few questions. Please feel free to unmute yourselves and ask the questions. Okay, if not, then let's end it here. Thanks, Aaratrick, once more.
Okay. Yeah.
And
Yep.
yeah, we end our limit camp over here. We hope to have more limit camps over the next few years, and I hope this competition goes on. So, thanks for your attention.
Okay. Thank you.
Aaratrick, very nice talk. Thanks a lot.
Thank
With
you.
no background with no background of three groups. Lovely. Really enjoyed it.
Thank you. Yeah.